your audio for it. Hello.
Yes, yes, sorry. Okay, hello, welcome to a new virtual tour in the European Saturn Observatory, or simply ESO, by its acronym. My name is Farid Char, and with the producer Felipe Zurita, we are going to be your guides in this virtual tour in La Silla Observatory. Okay, so a little bit about me. I am one of the tourist guides of the Paranal Observatory for more than 10 years, and I have some relevant experience in astronomy outreach for many years. And as I told you already, I am not alone. I am with the producer Felipe. So how are you, Felipe?
Hello, Farid. Hello, everyone. My name is Felipe Zurita. Today, I, I, I am the producer. I will show you the wonderful world of La Silla Observatory. I have a degree in astronomy from La Serena University, and I love share science and astronomy with people. Feel free to leave your questions, comments about astronomy, about you see in this particular Saturday guide, or where we are showing you, and leave your comments in the comment box. We have the first one, hello from Netherlands too. So let's get started for it.
Yeah, sure. So thank you very much, Felipe. Well, of course, ESO wants to be with you during these virtual visits and bring astronomy directly to your home or wherever you are. So during this tour, we will have some time for questions and comments. So we are going to dedicate some time later for that. Okay. Okay. So right now we are going to start immediately, and we are going to um, start by introducing and explaining a little bit about the organization, about ESO. Okay. So ESO is an intergovernmental organization composed by 16 member states. Its headquarters are located in Germany, and also Australia has joined ESO, but in this case as a strategic partner. In the case of Chile, well, is the host state and is the home of all ESO observatories. So, more or less from the 60s, and with those objectives in mind, ESO did choose one of the best places on the planet for astronomy for astronomical observations, the Atacama Desert in Chile. So around that time, Chile had started exploration campaign in order to explore and study some sites to attract international observatories such as ESO to our country. So in that way, Chile offered its territory, and ESO did choose the areas that seemed best. So the mission of ESO is basically to design, build, and operate astronomical observatories. Well, and what for? Well, to enable important scientific discoveries and incentivize the promotion and cooperation in the astronomy field. Now, in this picture, you can see the three observing sites of ESO in Chile. And first, we have the Paranal Observatory. This observatory is the home of the Very Large Telescope, or VLT. Um, right now, this is the most advanced ground-based telescope on Earth. Now, in the future, and next to Paranal, we will have the Extremely Large Telescope, or ELT, and this will be the largest visible light telescope on Earth. And near there, we will also have the CTA. This will be an array of different telescopes focused on capturing gamma rays. And also we have Chajnantor. Chajnantor is the site of the ALMA radio telescope. So in this case, ESO is part of this radio astronomy observatory uh, alongside its international partners. And last, we have the observatory we are going to visit now is La Silla Observatory. This is the first observatory of ESO in Chile, and it's located in the region of Coquimbo, in the north of Chile, around 2,400 meters above sea level. So we are going to visit this place during the next hour. So we are going to start this virtual trip with our planet, okay, in this screen. And we have to start this journey from Europe because ESO is an European organization. And on this map and outlined in white, we can see the different states that right now are ESO members. Chile, in this case, is participating as the host state and is the home of all ESO observatories. So, in order to know more about them, we are going to travel to the Andes Mountains, to the Atacama Desert in Chile. So, now we are moving around the Atlantic Ocean. So, I can tell you a little bit more about the mission of ESO. So, in order to understand this, the main work of ESO is to imagine what kind of instruments we need to study the universe. So, ESO is in charge to design the pieces, to build the telescopes, and to operate those telescopes to attend observation requests from different countries. So in this case, we can enable and incentivize the promotion and cooperation in the astronomy field. Okay, we are already there. This is a representation of the La Silla Observatory. So if you look carefully, well, the shape of this mountain, it's somewhat similar to a horse saddle. So that's why the name of the mountain, okay, La Silla, okay, because it's a horse saddle. Okay, so in this in this drone view, we can see the different telescopes located in La Silla. We have 10 telescopes right now in operations. Many of them are remotely operated, so we can control them from other countries. And two of them are operated directly by ESO, the NTT and the 3.6-meter telescope. La Silla was inaugurated in 1969. Okay, so and this observatory is it was chosen around in the 60s. Okay, so right now we are almost there. We are in the 3.6-meter telescope, and I remind you that all those telescopes are optical telescopes. Okay, so basically they are using mirrors in order to collect visible light and to send this light to some kind of instrument, okay, an astronomical instrument. Okay, so right now we have a different view here because this is a 360-degree view. Okay, so in this view, I can show you, for example, that these are the telescopes we saw a few moments before in the drone view, and this is the horizon. So you can see we have the sunset there. So this is like the typical view from the Atacama Desert, but of course, well, in this picture we have some clouds, but of course, most of the time is completely clear. We have no clouds and we have no light pollution, and we have very beautiful dark skies. Okay, so this is La Silla, and this one is the biggest mirror, the biggest telescope in La Silla, the 3.6-meter telescope. Okay, so we are going to start by visiting this place first because this is the first telescope inaugurated here. So we are going to access right now the 3.6-meter telescope, and here we are. So this is the interior of the 3.6-meter telescope, or 360 Okay, well, usually the ESO, the La Silla staff call this telescope the 360 just because it's 360 centimeters. Now, this mirror, the 3.6 meter, around the 70s was one of the was one of the bigger telescopes on Earth. Okay, and right now we have a very important instrument inside. Okay, the name of this instrument is HARPS. This instrument is a highly specialized instrument because every night we are trying to look for exoplanets. I mean, planets orbiting other stars, okay? Other stars that are different from our sun. Okay? So, what can we see from the interior of this dome? Well, of course, it's a giant dome. Okay, it's a giant telescope. Okay, from the first floor until the dome, we have 25 meters. Okay, and all this structure, the telescope structure, equals to a 7-story building. So everything looks small from here. And in order to give you an idea about that, there is a person standing there. So I can show you. This is the person. So you can understand how big is the telescope in comparison. Okay, so this is a useful reference to understand uh, more about the telescope. And right now I want to show you something. I want to display a picture because I want to mention the different components of the 3.6 meter telescope. Okay, so for example, in this picture we have in dark blue here we have the structure supporting the telescope. This structure is called the mounting. Okay, and this mounting works as a big arm uh, holding the telescope and providing the motion to different parts of the sky. So about this arm and parallel to the Earth's rotation axis, the telescope moves to follow the objects in the sky during the observation. Now, if we look up there in, let's say, light blue, we have the telescope's body. Okay, so basically in this structure, we have the primary mirror here of 3.6 meters or 360 centimeters, and the secondary mirror. Okay, so maybe you are wondering, where is the main mirror? Where is the primary mirror? Well, in this case, we cannot see this mirror because at this time in this picture is protected, is covered by its protection system, and this is this black structure. Okay, this is a system of tabs that can be opened or closed to protect the mirror against dust or humidity when the telescope is not observing. Okay. Now, in the tubular structure right here, we have the secondary mirror, and the secondary mirror is, let's say, collecting the light that first arrived to the primary mirror. So the light comes from the star, is going to the primary mirror, and because this primary mirror is concave, like a spoon, the light will be concentrated, will be reflected to the secondary mirror, and the light will be reflected again, and this light will pass through this hole in the center. Can you see? So we have a hole in the center, and this physical light can pass through this hole in order to reach the main instruments. Okay, so that's why you need to pay attention, because the mirror, the primary mirror, is like a donut, okay, because we have a hole here. Okay, okay. And where is the instrument? Well, the instrument, in this case, HARPS, the exoplanet hunter, is not visible because it's completely isolated in another room, in another floor of this building. So the 360 started operations in 1977, and it was a big challenge for engineering, and it represented the big mission of ESO as an organization from its beginnings, because European astronomy was collecting more effort from different countries in order to build an optical telescope in the 4-meter category. This was the biggest and more advanced category available at that time. Okay. Now, why it was necessary a telescope like this, so big? Well, in astronomy, we analyze our objects through its light. So the more light we collect, the more we know, the more we learn about them. So in this case, if we have a bigger mirror, we can collect more light, and of course, we will have more available information to analyze. So we can observe fainter objects, and we can distinguish more little details. Okay. Now, if you want to take a look at this telescope when it's moving, well, we have a short animation to show you that. Maybe we can show the. Okay, thank you. So, well, let's say that a mirror for astronomy is not an ordinary mirror. Its shape and surface has to be perfect in the level of fractions of millimeters. Okay. In order to achieve this in the 70s, it was necessary to build an extremely thick mirror. So the mirror here, the primary mirror, is 53 centimeters thick. But also, something important, if you have a mirror that is so big and so heavy, okay, well, in this case, the mirror has 11 tons, okay. This is the equivalent of two African elephants, okay. So this is the main consequence. We have a big mirror, okay, we have a thick mirror, and of course is a heavy mirror, okay, 11 tons. Now, if we want to build bigger telescopes, even bigger telescopes, we need to find different solutions. Okay, so the next step in order to build bigger telescopes, you can know more about that when we visit the NTT, the New Technology Telescope. Okay, because in the New Technology Telescope, we were able to do some progress, some improvements in order to build bigger and bigger telescopes. Okay, so that's all regarding the 3.6-meter telescope. Okay, so we are going to come back to the outside, because the next stop will be the NTT, the New Technology Telescope, that is located here. So this telescope, of course, is different. Okay. Now, I don't know if just before going to that telescope, do we have any question, Felipe?
Farid, we don't have any question. Remember, for people see us, leave your comments, question about astronomy, the telescope you see about the 3.6 is the first one, or about astronomy. Whatever you can ask everything about astronomy or science in these places. So feel free to leave your comments. Any question is sorry, you can leave this.
Yeah,
Only
it's,
have greetings
any
for a
question is
hamster
important.
that you say, but I we don't have any questions. So you can go to the NTT telescope.
Okay, thank you very much, Felipe. So yeah, we are going to continue, and right now we are going to continue with the next telescope, the NTT. So Before going inside of this telescope, I want to mention the differences between the domes. You need to think that both telescopes here, they have a mirror that is more or less exactly the same diameter. And you can see that this dome is much bigger than this one. Okay, well, maybe it's not too easy to appreciate this difference, but this dome is much bigger than this one. Okay, but remember, the main mirror is more or less exactly the same. So the NTT was inaugurated in 1989, and the dome is, let's say, small. Okay, small and compact. The design is octagon. Okay, and there is a system of flaps. So this represented at that time an an evolutionary leap in the construction of telescopes, because it allowed to host some instruments in smaller and lightweight structures, and much more efficient in terms of the, let's say, the airflow in the interior. So that's why the big and complex domes like the 3.6 meter here, well, let's say that they are more obsolete right now. Okay, so basically, this telescope, well, that's why we call this telescope the new technology telescope, because we were testing different kinds of technologies for the next generation of telescopes. Okay, okay, so we are going to access right now to the NTT. Okay, if you remember the structure of the 3.6 meter telescope, well, the big dome, and this, and you can remember that there was a person there, and the person looked very, very small if you compare with the telescope. Okay, but in this case, this building, the building of the NTT, the New Technology Telescope, is more or less attached to the telescope. The telescope is right here. Okay, so if we try to um, stay just next to the telescope here, okay, we will be more or less like this size, because you can see there is a door here, so you can imagine more or less the size of a person. So you can see that this telescope is much more compact. Okay, so it's not like the 3.6 meter telescope. So in this case, it's very simple to notice that this dome, this structure, is more compact. I will show you from the other side. It's more or less the same, but this is the entity from the other side. Okay, so from this telescope, something important, the mounting of this telescope is also completely different, because in this case, when you want to rotate the telescope, well, all the building rotates. Okay, so basically this kind of rotation, okay, is involving the dome of the telescope, okay, and the telescope. So essentially, all the building moves and all the telescope is rotating. Okay, that's why I say that the building is attached to the telescope. Now, from this location, you can notice the main mirror of the entity. It's here. Okay, this is the main mirror, and you can see that this, maybe you can see that it's a concave mirror. Okay, so this disc is the mirror, and we can see that it's reflecting a little bit of light. Okay, so if you remember, the 3.6 meter mirror has a 53 centimeters thickness. Well, the mirror in the entity is more or less the same. The diameter of this mirror is 3.58 meters, to be precise, and is much lighter. This mirror is only 25 centimeters thickness, and the weight is only 6 tons. So this is like the equivalent to just one African elephant. So in order to keep the shape of this mirror all the time intact, okay, the entity is integrating and very interesting technology, because you need to remember, you need to understand that the 3.6 meter mirror and the 3.58 meter telescope the mirror in the entity are anyway very heavy. Okay, so when you have a heavy mirror and a concave mirror, you need to be careful with, because just because of gravity or physics, the concave shape can suffer some deformations. So if your mirror is suffering some kind of deformation, the quality of the final picture will be affected. So we need to do something in order to avoid this problem, in order to correct, to compensate this kind of distortion. So our solution in the entity was to incorporate a kind of pistons underneath of this mirror. So this kind of pistons, the technical name is actuators. Okay, we have 75 actuators just below here underneath of this mirror. So the actuators are providing a small pressure. Okay, so the different portions of these actuators will push the mirror, okay, just a little bit, in order to compensate any kind of distortion in the concave shape. So the result of this is that we are trying to preserve the same concave shape all the time, regardless of if the telescope is rotated, tilted in any position, because we have the actuators doing this pressure. Now, all of this system, this technology, is called active optics, because we are doing some kind of, well, active action on the mirror. Now, this actuator system is controlled by computer, okay? So it's automatic. This active optics technology was developed by ESO, and it represented a technological advancement, and it was fundamental for the construction of the next generation of telescopes in the 10-meter category. Today, we are using this technology in all modern ground-based telescopes, including the Very Large Telescope, or VLT, in the Paraná Observatory, and in the future in the Extremely Large Telescope, or ELT, that right now is under construction near Paraná. Now, where are the people? Where are the scientists that are working for La Silla? Well, in this observatory, we have approximately 30 people, okay? Not a lot of people. And all of them are, well, they have different kind of jobs in the different telescopes. But in particular, the scientific staff and technicians are located in a control room. So they are not exactly here at night. So nobody is here at night. Nobody is inside of the 3.6 meter telescope at night. All the scientists, all the astronomers are located in a dedicated control room. And this is basically another building. It's located in another place of this observatory. And we can see in a few moments, we will see a time lapse of a typical night operations from La Silla Observatory. So you can see here, let's say, two separated workstations. One workstation is for the entity, and one workstation is for the 3.6 meter telescope. So I think that the workstation to the left is for the entity, and the right workstation is for the 3.6 meter. And you can see that they are essentially several computers for different purposes, and you need only a few people working there. So you don't need hundreds of people working in the night operations. You just need a few people working there all night in order to supervise the observations. Okay, so we are going to continue, and because right now you know already a lot more information about the observatory and the people working here. Now I want to invite you to take a look, to review some of the main scientific milestones made possible from all ESO observatories. I mean, La Silla, Paranal, and Chajnantor. So you will see how astronomers from all over the world are using those telescopes to study objects close to our home, the solar system, but also others that are located in the more distant places of our universe. So now, please take a look at the top 10 list of the main scientific milestones from the ESO sites.
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when two independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Okay, so this was the top 10. I hope you enjoyed. But we have something else. We have an extra result, something like a bonus track. So we are going to check this quickly. It's not exactly recent news, but it's very important. A team of astronomers was able to capture the first picture of a black hole. So the Event Horizon Telescope, or EHT, an array of 8 ground-based telescopes distributed across the planet, and thanks to an international collaboration, was able to achieve the first direct evidence, visual direct evidence of a supermassive black hole. So you will see a picture with the black hole in the center of Messier 87. This is a massive galaxy in the nearby galaxy cluster of Virgo. So this black hole is located 55 million light years from Earth, and its mass is 6,500 million times the mass of our Sun. Okay, so we are going to continue with something very, very interesting. And by the way, the top 10 and this news about the black hole is just a sample of the several discoveries from the ESO telescopes distributed in the north of Chile. Well, so in this picture right here, we can see La Silla at night. So this is very, very impressive because you can see how the night sky is beautiful, of course. In this case, this picture, you can see there is no moon, and you can see a lot of stars and the Milky Way. So in this view, we have the NTT, and next to the NTT, to the left, we have a very popular constellation, okay, very near horizon. This constellation right here is Orion. See, so Orion is the big hunter, and those 3 stars, somewhat aligned, are very popular feature. Is called is representing Orion's belt. Okay, in Spanish, this is known as las Tres Marías. Okay. So basically, this is a very popular feature of Orion, and it's very easy to recognize. And this constellation is visible from the northern hemisphere and the southern hemisphere. So anyone can observe Orion. Okay. And also there is another feature here is the Great Orion's Nebula. So this is a star-forming region and is very, very bright. So you can see this feature even with your naked eye in a dark night. And of course, with binoculars or even a small telescope, this is very, very impressive. Okay. Now, if we continue, we are going to move um, up there because next to Orion, we have a very interesting star. Um, Here, we have the brightest star in the sky. This is called Sirius. Okay, so Sirius is the brightest star in the sky, and it belongs to another constellation that is called Canis Major. And in the mythology, Canis Major is one of the hunting dogs of Orion. Okay, so basically, the constellation of the brightest star in the sky is connected in the mythology to Orion. Now, if you look closely, you can see that all this area of Orion, the Sirius, is next to uh, this path of light. Okay, so this area, as you can see, we have much more stars. Okay, we have more concentration of stars if we compare with this area or this area. So that's why this is because this is one of the arms of the Milky Way, our galaxy. Okay, so our galaxy is visible, is clearly visible in this location in the Atacama Desert, and you can see that it's not only about more stars. We have also star-forming regions. We have nebulas. We have dark clouds here. So you have a lot of interesting features that are visible from the southern hemisphere. So this is the typical landscape here in, in the Atacama Desert, and depending on the season, you can see different areas of the Milky Way. Okay, okay. So we are going to come back to the horizon, but we are going to change the view because I want to show you something different. I want to show you another area in the sky because right here you can see two spots in the sky. Okay, so those spots are something called the Magellanic Clouds. So you can see the large Magellanic Cloud here and the small Magellanic Cloud there. So the Magellanic Clouds are basically galaxies. They are irregular galaxies, and its name it comes from the first written records from Ferdinand Magellan during its circumnavigation of the planet in the 16th century, because at that time no one has any idea about well what a galaxy is. So in the records, those features, those objects, were annotated as clouds. But today we know that they are galaxies, they are satellite galaxies of the Milky Way. So they are orbiting our Milky Way. And something interesting is that those objects are only visible from the southern hemisphere. So you cannot see those objects from well from Europe or most of USA, etc. So you need to be in the southern hemisphere to look at the Magellanic Clouds. Okay, so if we continue here, we can see also right here the smallest constellation in the sky, the Southern Cross. If you look carefully, it looks like a cross, right? It's a little bit tilted. Now, this is another constellation that is only visible from the southern hemisphere. And in this case, it's the smallest constellation in the sky. Now, there is an important, how to say that there is a practical use for the Southern Cross because in the southern hemisphere we don't have any bright star next to our south celestial point. Okay, in the northern hemisphere you have a very bright star called Polaris to show you more or less the location of the north celestial pole. Okay, the celestial pole is basically a projection of one of the Earth's poles in the sky. So in the southern hemisphere, we don't have any bright star there. Okay, so in order to locate this point, the south celestial pole, we can use the Southern Cross. So basically, we have to project the longer stick of the cross about 4 times and a half. So we can project this 1, 2, 3, 4 and a half, and more or less like here, we will have the south celestial pole. So if you, for example, if you take an astrophotography toward this direction for, I don't know, for a long exposure picture, you will see some circles, some concentric circles there, okay? Because this is a projection of the south geographic pole. Okay? And if you look at the horizon, if you focus your view here and now you look to the horizon toward this direction, you are basically looking at the south cardinal point. Okay, so that's the importance of the Southern Cross in this context. Okay, now I want to finish this explanation, so I will come back to the 3.6-meter telescope, and I will show you finally here that just below of this telescope and rising over the horizon, we have the center of the Milky Way. So this area, as you can see, is much more complex. You have a lot of stars and dark nebulas, and we have the Scorpius constellation. So you have a lot of different fissures, okay? And this area is very interesting because it's very popular for astrophotographers, okay? Because from the southern hemisphere, during winter months, I mean winter months in the southern hemisphere, I mean May, June, July, we are able to observe all the Milky Way in the sky, okay, all night. So we can see the entire Milky Way. And I know that this is different from the northern hemisphere because in the northern hemisphere, observers can only look at more or less, I don't know, 75% or something like that. But in the southern hemisphere, you can see the full Milky Way. So this is what happens here. We have the center of the Milky Way rising. And in order to, well, almost finish with this explanation, I am going to show you another view of this mountain top. Well, this is another view of the night sky from the mountain top. And I want to show you this very quickly because this is the 3.6-meter telescope. But we have something here. This is light pollution. The light pollution, just to tell you quickly, is a big problem for astronomy, okay? Because, well, it's a problem for any astronomical observatory, and we need to protect, of course, the night sky. So in Chile, we have some legal rules in order to avoid light pollution in the sky, especially in the Coquimbo region or Antofagasta region. So at this moment, this is not a problem, but of course we are trying to protect our skies because, well, of course, this is part of our natural heritage for all the mankind. So this is why it's so important to pay attention to the problem of the light pollution. Okay, and now I want to rotate the view because we have the perspective of La Silla telescopes, and I want to show you just one last
We have
picture here.
a particular question.
Yes.
I have a question for a user seals today. What is the distance from Earth to Magellanic Clouds?
Oh, well, the Large Magellanic Cloud is about
I remember
160,000 light
Yes,
years.
160,000 light years.
Yeah, and the small Magellanic Cloud is more far away. It's like 200,000.
2,000.
Yeah, 200,000 light years. So yeah, of course, it's very far away, but
Mm-mm.
it's still our nearest companions because then you have, for example, Andromeda galaxy, and this is 2 million light years.
Mm.
But the Magellanic Clouds are much closer.
This is the little question we have for user 123 CEOs. Thank you for that question. Remember, you can leave your question whenever you want about astronomy. So continue, Farid.
Yeah, okay. So now we are looking at the road, at the little road connecting all telescopes in La Silla. And you can see that we have different telescopes here, okay? And eventually we will reach the hotel, the hotel in La Silla. So the hotel is basically the place where the astronomers and the scientists and all technicians can rest during its um, shift in La Silla, because the people are working in a shift system. So in this picture, for example, we have a perspective of this place. This is the hotel. And this person here is the photographer who was in charge of all the beautiful pictures we saw today. And something very interesting, because as I told you already, from the southern hemisphere, we can see the full Milky Way. So I can show you that this picture, for example, was taken during winter. And you can see here exactly that. You can see all the Milky Way, the center of the Milky Way in the zenith. So this is a very, very impressive view. And that's why many astrophotographers enjoy coming to the north of Chile, for example, to take astrophotography and to observe the night skies and to go to astronomy tours and visit some professional observatories sometimes. Okay, so this is basically the explanation, the general explanation about the Silla. So I don't know, Felipe, if we have any last question or comments.
We don't have any an important question. Thank you for seeing us. This is every Saturday we have a virtual tour. This Saturday is from La Silla, and the next is maybe is will from Paranal. Every Saturday I can read your question. If you don't have any question today, maybe you can have a question from the next Saturday. So I hope I see you in the next virtual guide and virtual tour. Sorry, and thank you for seeing us today. This is
And
all
thank
I
you.
can say.
Thank you. So, well, of course, I want to remind you that all this visit information and pictures is available on the ESO website. So you can take a look and know more about the information and about the pictures and videos from the ESO website. Okay, so thank you very much. We invite you to visit and to attend the next virtual tour. It could be Paranal or La Silla, Spanish or English. So thank you very much on behalf of PISO, and have a good day.
Bye
Bye
bye.
bye.